The nucleation. Okay. Have you watched the video?
Yes.
Okay. So which part that you don't understand?
How it initiate the crystallization.
How it's initiate the crystallization. Okay. Nucleation. Right. Okay. This part. Are you clear? Nucleation. How can I start? Um. Nucleation. Can you differentiate between homogeneous and heterogeneous nucleation?
Yes, sir.
You can differentiate. Okay. So how it starts? All right. So for nucleation, to start the nucleation, there are three stages. Okay. Not three stages. The condition. Okay. Let's say. Okay. Of course, for liquid to solidify, is a require of reduction of temperature. Okay, the reduction of temperature. So depends on the uh, mechanism of nucleation. Either it is a homogeneous or heterogeneous nucleation. It will prefer the easier one. Okay, the easier one compared to heterogeneous. Homogeneous is more difficult. Okay, because it requires supercooling. So therefore, this supercooling is a temperature which is below freezing temperature. Okay, to decrease the kinetic energy of particle. Uh, because if the particle has a high kinetic energy, so mean it tend to remove the bonding. So it does not enough if the temperature reach the uh, freezing temperature. Okay, as you know that if we heat our materials, if we will reach melting temperature, which is this is temperature versus time for cooling curve. Okay, uh, when you increase temperature, it will reach the melting temperature. It will start to destroy the bonding between the atoms. And at this point, even you keep heating, the temperature is not rise. But what happened is the kinetic activity, it's transferred into kinetic activity, and the temperature is not increased. Okay, so the atoms receive kinetic energy and to break the bonds, and after it break the bonds, and the temperature can increase. Okay, so opposite to cooling process during solidification, what happened is if you reduce the temperature, it's not straight away like this, meaning that just contrary to the heating or melting process. But when you reach this freezing point, okay, freeze, which is Tm is a similar temperature to the freezing point during the solidification, right? What happened is you don't have enough kinetic energy. You don't have enough lower temperature to stop the kinetic energy. What you need during the homogeneous reaction is reduce the temperature, lower the freezing point, and we call it supercooling. All right, we press the kinetic energy by more reduce the temperature. Then what happened is the atoms start to move and they tend to form a bonding between one another. Okay, so if it's close to enough to form a bonding, and it start to form a nucleus. Okay, a nucleus, to form a nucleus you require numbers of atoms. Okay, okay, during the supercooling process, okay, which is we enlarge this region to this one, right? So this is melting temperature. So this is supercooling temperature. Okay, slightly lower than the freezing temperature. So what happened is it start to grow, okay, during this point, and it will stop at this point and increase the temperature, and because apa tu, release heating during the solidification. So that's the reason temperature rise, meaning that this is maximum reduction of temperature or maximum supercooling temperature, which is allow the formation of nucleus. Until it form at this point, it form enough numbers of atom, and then it start to form a nucleus. When it's formed a nucleus, before this, what happened is the number of atoms is not enough. Maybe if you zoom out, the particle size is not enough to call this as a nucleus. But this one, at this point, it reaches sufficient numbers of atoms, and we can call this as a nucleus, and it start to grow larger. So this is a concept of nucleation during homogeneous reaction that requires supercooling. Okay. Uh, is that enough? No? What else?
Okay, doctor, understand.
So once it's from nucleus, all right, the atom, just because of the interaction between one atom with another is strong enough at the nucleus, then it will attract more atoms. Because remember, metal, it has, for example, nickel, it have two free electron at the valence. So these electrons are eager to form another bonding to stabilize is condition, because the electron has a less interaction with the center of the atoms, okay, the electron. So remember, once we have, okay, one we have a nucleus, okay, there's a lot of atoms inside, and the electron is forming the electron C. So atoms from outside with the two electron valence here, for example, this is nickel 2 plus, and not nickel 2 plus, nickel in the metallic state, it has a two electron at the valence. Of course, because of the strong bonding of metallic atoms here, this atom tends to form uh, 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 bonding with where the electron tend to form the C electron in the nucleus. Then it will grow larger. Okay, it will grow larger until it form a grain. Okay, in metal, remember, the solid form of materials in metal is in the form of grain. Yes, so then it will grow from the nucleus, become grain, and grain with another grain will form a grain boundary. Where is grain boundary? Is somewhere here. Okay, the interface. Okay, the boundary between one grain to another grain. Okay, what else? Soalan lain tak?
Doktor, ada lagi
Ya,
satu soalan.
apa dia?
Can you explain the dendritic crystal growth?
Dendritic crystal growth. Okay. Dah tengok video pun tak faham lagi Okay ke? Masih tak okay lagi Alright. Let's go to the. Okay, dendritic crystal growth. Okay, so okay, dendritic crystal growth is happen if we look at in the casting. Okay, where is the casting structure? This casting. Okay. Casting. Okay, dendritic crystal structure. Okay, at first it will form chill zone somewhere here, chill zone at this columnar and chill zone at the area close to the mole. Okay, and then it will form the dendritic crystal structure. Okay, somehow the area close to the mole, okay, the reaction is quite fast and it tends to form at direction opposite to the heat release. Okay, heat release. So and after that it quite stable and it's easily to form branches. Okay, unlike the one columnar structure at this region near to the mole. Okay, it doesn't form dendritic. Okay, for the dendritic, okay, imagine if they have what we call it, like a tree. Okay, like a tree. When a branch grow, okay, it will grow larger and larger, and it try to find one region, okay, to to grow. Okay, similar to the dendritic, it will uh, start with find a one area where it can release the energy, so it will grow to this direction and forming to the more surface area, the faster the energy will release, which is heat energy. So this is how dendritic react. So branches tend to form from the first solidification surface, which is columnar surface. Columnar surface is um, this region, columnar region. So once we have the columnar region, they start what the first solidification at this region. Okay, it start to slowing down in terms of cooling rate. So at this stable condition, dendritic will form. Okay, and it will form similar to the how the tree grows, uh, which is the branches of the tree itself. Okay. Apa lagi nak terangkan So this is how the dendrite is looks like under the microstructure. So you may see that it's forming like a the branch of the tree. Okay, I have shared the tutorial in the WhatsApp group. Okay, please look at the WhatsApp group. There is some additional tutorial questions related to topic 1 and 2. Maybe topic 2. Okay, this one, right? You may try solve this problem. Okay, please have a look the question at the WhatsApp group. I posted in the WhatsApp group. ions, okay, at location 000 and cesium cation at half half half. Okay. All right. So this one at the center is Cl, and half 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 somewhere in the middle we have Cs. So this one is Cl, 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 and Cs at the center. Okay. Nak suruh saya jawab ke? You boleh try lah. Okay, this is roughly the question asked you about this problem. So Cl and Cs. Okay. So this is an example of how inorganic compound, okay, having a crystal structure in the solid form, Cl minus will act as an ion, chloride will act as an ion, and cesium will act as a cation, and the position of Cs at the half half half. How do you locate this cesium? Of course, let's say you assign this as origin 0, 0, 0. So half is, let's say this is X. So X is here, Y, and Z. All right. So half to the X and half to the Y and half to Z. So what is the structure for this one? Anybody? What is the crystal structure for this one?
Body centered.
All right, good. So you can draw and label the content like this. Okay. What is the chemical formula? Okay, you try solve this question first. Okay, specify and draw the Bravas lattice motif that define this structure. Okay, and then for plane 111 of this cell, draw the representation of its atomic packing, and then for plane D, which family of direction is referred as a closed pack direction. Okay, name one direction which is perpendicular to its planes. Okay, you need to know, okay, when it's given Miller index like this, how to draw the plane. Okay, how to draw the plane for Miller index like this. All right, so it has a intersection X at 1, Y. Therefore, we got a plane like this, and draw the direction. Okay, direction that refer to the as a closed pack direction. Why is it closed pack? Because it's contained one atom here, one atom here, one atom here, one atom here, and one atom here. This is the most closed pack plane compared to the other plane. Or which one? For example, if we take a look at, oh, tak boleh tukar color. Okay, if we look at this plane, for example, okay, it's contain 1, 2, 3, 4. It is not packed enough. Close pack is the one plane in yellow. So for plane D 110 is why it looks like this, because the infinite intercept at Z direction. Okay, so at plane D you need to write name one direction that is perpendicular to this plane. So you need to think what is the Miller index for direction. x like this. You should find this x, y, z for this one, the plane. Okay, and then solve this, the density, and try it first. Okay, I give you exercise this for this, and try to answer this. Okay, for this question. Okay, uh, okay, it's okay. You can Google to help you to understand. But the thing is, you need to know about the planes. You need to know how to index the direction. Okay, you need to know how to determine the density, and if a given position based on the coordinate inside the unit cell, how to locate the atoms inside the unit cell, and that's it. Okay, try to do this exercise, and if you don't understand, you can just text me. Okay, so any other question?
No, doctor.
All right, what about the assignment? It should be due by today, right?
Yes.
Doctor,
So do you have any problem?
Doctor, for assignment we have to just draw the scales, right?
Yeah, yeah.
Just scales, not any definition or like that.
You need to draw the not plane direction.
Just direction, right?
Yeah,
Okay, doctor.
not plane, because the question give this kind of Miller index x, y, and z. Not this one. This one is plane. This one is direction. Okay. Remember, when you write or draw the planes, or when you draw the planes, okay, let's say you have this uh, direction, for example, like this one. Okay. Uh, yeah, of course, you need to label properly for the axis y, z. Okay, but this one is not actually correct if you don't put the scale here, the dimension properly. For example, what is it? Is it 2/3 or is it 1/3? Okay, so if it is 2/3, okay, you need to define the origin. Let's say you said this is the origin. Okay, if you put 2/3 means the distance from here to here is 2/3. Okay, you need to define the origin. Define the origin here. Okay, you cannot just leave as a blank like this, because 2/3 can be from here to here. Okay, define the origin. Okay, so to define the origin, if it is not at the location of normal origin, which is here, so you need to write it like this. This is origin, or you can label it as 0, okay, without this, and then redefine XYZ direction. Okay, of course, Y, this is negative. Okay, this is Z, right? You need to define the origin. Then, if you draw an arrow like this, you just put as 1/3. It is correct. Let's say you don't put this origin. What you can do is, okay, you just give a proper dimension. For example, you draw this arrow and you write this distance from here to here as 1/3. Okay, maybe you forgot to put the origin here, but it's okay if you put the scale, proper scale, like this one. Okay, 2/3. Okay, from where to where, the distance, the lattice, the portion of the lattice. Okay, whether it is the direction at y direction is equivalent to negative 2/3, or you must to write a proper label in the crystal structure. Okay, don't just simply give a empty. Of course, if you don't have this fraction number, it's okay. the answer may correct. But if there is a fraction number like this, okay, you need to label properly. Okay. So any other question? Any question regarding to the assignment?
No.
No. Okay, fine. Have you scanned the attendance?
Yes.
Yes, doctor.
Semua dah? Semua dah? If you are not yet scanned the attendance, you may scan now. Meanwhile, please, if you have any more questions, we can discuss. Tak ramai tempat Khamis ni. Okay, let's continue. All right, for diffusion in solid. Okay, diffusion is part of the yeah, when during the solidification also is considered as diffusion also, when atom diffuse in a position to form yeah, it's a diffuse in the molten materials until it form a solid. Okay, so it's something, a movement of atoms into a position. So that's the reason diffusion is taking place in the third part of this module, right? The outcome from this lesson is you should be able to understand how diffusion occurs and what the driving force behind it. And besides, you should understand Fick's law and what factor will determine the rate at which diffusion occurs, and understand the effect of microstructure on the diffusion. Okay, we have learned about microstructure earlier. Okay, how during the solidify is formed a grain, and also inside the grain there are different types of grain. There are some columnar, chill zone, equate zone, in the one single cast materials. Okay, there are different part, different structure, different grain, even though it is the same materials and the same cast materials. So it has influence in terms of diffusion based on the different microstructure. All right, diffusion is a process of mass flows from one place to another on an atomic or ionic molecular level. In a solid state, diffusion can be defined as the movement of atoms within the atomic network by jumping, okay, from one atomic site. Okay, why do I need to know this? Okay, imagine, okay, there are container containing different types of gas. If the gas is able to diffuse through the container, what will happen? Okay, so we need to understand the diffusion behavior of the gas inside the tank, and the behavior whether or not it will passing through the container. If yes, how long it takes? Is it possible to yeah, even though it is a still, if there is an atom diffuse from the outside, atoms of oxygen diffuse from outside, or the gas inside the container diffuse from inside to outside, what will happen? Okay, so that's the reason we need to know about the diffusion behavior. Okay, for example, let's say we have a steel and there are some corrosive gas inside. Okay, because of very high pressure, the one spot of crack will propagate, become larger. If the gas inside the container is toxic, it will fasten the crack formation and crack growth. And beside, based on the knowledge of diffusion, we can use the diffusion concept in making the gear achieve a certain properties. Okay, for example, if we produce a gear uh, from cast iron or from the aluminum or from the steel, okay, we meet a requirement of yeah, of course there are a certain standard set for the function of this gear. Okay, for example, it must be strong, carry load, can sustain the cyclic load. However, when the gear do the works, it has a connecting with a neighboring gear, okay, something like this. So it has some kind of um, uh, it do the function that's experience friction at the interface, okay. The connecting area of the gear experience friction. So initially we design it as strong, so high toughness material. So this kind of material basically is not hard. This one is not hard. This material is not hard. If we require a resistance to friction, the surface must be hard. So what we can do, we diffuse the carbon atoms on the surface of gear. So it is a concept of diffusion. How much we can diffuse carbon into this material. What is it? Maybe iron carbon, maybe aluminum, we don't know. Okay, it depends on the application. So diffusion can apply. Theory diffusion can apply for this kind of properties improvement or a strengthening mechanism of the component. So how actually do the atoms move between atomic site? Okay, because remember diffusion occur at the atomic level or molecular level. All right, when there are no defects in crystal lattice, atom cannot move from one side to another side. Okay, all atoms have thermal energy and constantly vibrate in their stable position. Okay. So, however, in real materials, it is will always have defects such as vacancy. This is defect. Remember, yesterday we learned about defects. Okay, this is vacancy defects. So all the time, the vacancy will be present in the material. So this will become a starting point for the diffusion to occur. Okay, so one atom move to another position because of the um, presence of vacancy. But for this atom to move from one position to another position, okay, it must push the atoms. Okay, sekali. Okay, all right. There is a vacancy next to these dark blue atoms, but the gate needs to passing through this this gap between the two atoms. Okay, so it need to push the atoms to allow it to move from its original position to the vacancy. So to do that, it requires activation energy, and where it can obtain the activation energy basically from the heat. Okay. Uh, so how actually atom move between atomic site? Okay. So based on the energy diagram, okay, this minimum lower position, okay, indicate the stable atomic site. Okay, it's feel comfortable at this position because it doesn't do any work to allow it to be there. Okay. However, if it has high energy, okay, so this maxima position in this amplitude indicate that the energy that the atoms required to move from one side to another side. So to passing through this, okay, if, because yeah, if it has an energy coming from externally, so it can really move from one side to another side. Okay, for this example, it is not vacancy, but it is a gap between the atoms. So if it receive energy from the outside, it become able to squeeze this atom. Okay, and then it can move to another side. Okay, and then it's indicate the stable side. So meaning that this is a stable side because it doesn't need to push any atoms. Okay, and so forth until it move to, once it receive energy, it will move. It will move because it have energy to squeeze the other atoms to allow it to move to the another vacancy region. Okay, the height of the barrier is known as the activation energy. If an atom has enough thermal energy, it can cross the barrier. So diffusion depends on temperature of the solid. Okay, depends on the temperature. If it is high melting temperature or low melting temperature, whatever the thermal properties of the materials. Okay, maybe a slight induce of heat can really excite the atoms, or maybe require higher, depends on the materials. Okay, so the mechanism how atoms move or diffuse. Okay, there are two. One is through the substitutional diffusion. Okay, where it's only happen for substitutional only happen if inside the atom, inside the material, there is a vacancy. Okay, so for example like this, and then it can move to another side. Okay, provided there are some external energy, which is thermal energy. So the rate of diffusion depends on two factors. One is how easily vacancy can form in the lattice, and how easy it is for an atom to move into a vacancy. Okay, it's really require diffusion. Let's say the material is during the solidification, it's the normal condition of that particular materials. One, it's solidified. The number of vacancy is huge compared to other materials, so that particular materials are able to be diffused with any foreign atoms. Okay, so interstitial diffusion. For interstitial diffusion, okay, it's something to do. If you recall yesterday's lesson, we talk about interstitial defect, something like that. So behavior, the atom, small atom is must be following the characteristic of uh, interstitial defects. Okay. Um, okay. It is not a lattice site where there is a missing atom, but instead it is an interstice, which is the gap between the atoms. Okay. The rate of diffusion depends on how easy it is for an atom to move into an interstice. Okay, so yeah, how much energy it receives to squeeze these atoms to the other side. Okay, it can move anywhere. There are abundant sites. So therefore, since this diffusion mechanism does not require vacancy, it happens more rapidly than substitutional diffusion. Okay, yeah, let's it's not difficult for the atoms to find to reach the vacancy, not vacancy, the empty spaces of the interstice, because the interstice is everywhere. So it doesn't require much energy. One is because basically for the interstitial defects, it is a small atom. Right, small atoms. And number two, it does not require vacancy, and uh, it is interstice is abundant. There are a lot of interstices everywhere between the atom. So because of high concentration of the space for interstitial diffusion, so interstitial diffusion will occur more rapidly. One is because of small, another one is abundance of site, okay, which is interstices. So how does diffusion happen beyond an atomic scale? Okay, for example, in the liquid. Okay, so diffusion describes the net movement of molecules from a region of their high concentration to low concentration. Okay, it's common sense. All right. Yeah. If you have a water and you drop the syrup, and that, yeah, something like this. Okay, you drop something yeah, cordial syrup, and the color will dissolve in the water, and it will go to the area where the syrup is less concentrated. Okay, so that means it will move from high region that containing high concentration, and it will move to the low concentration. Okay, molecules have kinetic energy and move in random direction. Okay, because there are a lot of empty spaces between the atoms. Okay, let's say you drop these syrups into a stagnant place or the water, and then it will move into a region where this A atoms is low concentration. So it will go to this direction, not stay at here. If you put it in the different concentration, it will go to a region, a direction that contain less concentration of its species. Okay. So for diffusion to occur, it's apply fixed first law. Okay, this is the fixed first law. J equal to minus D delta C over delta X. What is C? C is the concentration, and X is a distance. Okay, the distance from first, yeah, the distance from the what we call it, from the interface. Okay, from the interface. What is interface? Interface is antaramuka. All right, let's say this is your component. All right, so this is interface, where this is the diffusing agent. Okay, let's say you want to diffuse carbon inside the iron. Okay, you put a carbide around it, and then you heat it up. Okay, and you allow the carbon to diffuse inside the iron. So interface is here. Okay, so the distance is from interface to the center. Okay, from interface to the center. Okay, this is X. Right, so we only take, this is the substrate, the steel. This is the region of the carbon, so it will diffuse to this direction, and X is from here to here. This is X distance. Okay. All right. Steady state diffusion. Steady state means diffusion takes place at a constant rate. Constant rate. Okay. Concentration of atoms or molecule passing through the cross-sectional area remaining constant. This means that throughout the system, the concentration change over the distance only. Okay, if the concentration change over the times, that's not happen. It is equal to a zero, meaning that it does not change with the time. Okay, the diffusive flux is proportional to existing concentration gradient. Okay, example situation where you can use fixed law is in the plastic foil for tablet. Okay, like this. Okay. All right. Let's say you want to design a plastic foil for the tablet. Okay. Whatever the packaging materials. right? You must know that, okay, let's say this is the packaging. Okay, you put something inside and there is a environment here. You need to consider there is oxygen, there is a water somewhere. So you need to know how much this diffusion will occur penetrating this plastic container, or you need to think how much this concentration, okay, environment inside the plastic will diffuse to outside. Okay, if that's happen, maybe whatever the material degradation of this element, okay, uh, the 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 the, the medicine inside, okay, it will stable in its original form if the concentration around it maintained as at a certain of period. Okay, if there is a diffusion between inside to outside, or oxygen or water through this plastic packaging, you need to know how long it takes. Okay, how much, if that's happened, how long it takes, how much it will diffuse, okay, from a normal concentration of oxygen or water from outside, or the concentration of these gases or whatever the environment inside this medicine. Okay, let's say it's really some gases, it produce some gases around it, how much the concentration will passing through the plastic, so we can determine, okay, by using this equation where diffusion coefficient is a constant based on the material of this plastic packaging. All right, uh, depends on material of the packaging you can have from the database. And then the concentration, you need to know what is concentration from outside or concentration from inside. Okay, and then the distance can be measured, the distance, for example, like if you want to know, all right, okay, how long, maybe the application you can compare from, compare between material, one material, for example, materials X, and there's another material for the packaging which is Y. Okay, maybe there is some standard of diffusion flux you can measure. For example, it has a certain value of D, and this value is constant for comparison between X and Y. All right, you can determine which J is lower. Okay, we don't want a fast diffusion rate. Okay, if X is higher J than Y, so means we can select Y as a material for the packaging. So we can compare in terms of the value of diffusion flux, which one is slower diffusion. Then we can ensure that our selection based on the comparison study, the material is better, or we compare with the database. For example, the FDA uh, or the health ministry said a standard requirement for the packaging. So if we introduce materials, we need to know what is we can calculate the J. All right. What is X? X is the thickness of this packaging. So as an engineer, you can suggest what is the thickness for the packaging, what is the material. Materials based on the J or the D, not J, sorry. Materials, you need to know the D, and you can calculate the J, whether the J is following the standard set by the Ministry of Health, um, something like that. So meaning that based on this equation, you can make a decision what type of materials you can use for the packaging, and what is the thickness to make sure that the J value is following the standard. Okay. And if you want to propose new materials, you can compare which one is lower in terms of the value for the J. Okay. If let's say the X material is higher than Y, so you can select the Y. And when you making a comparison, make a comparison study, you need to set the objective. If you let's say your boss asks you to reduce the cost, okay, let's say the supplier propose cheaper materials, you can make a decision by following this diffusion situation of the plastic packaging. Okay, you can use this as one of the application for this theory. Another example, when we want to apply this knowledge, usually when we do a process named case hardening, okay? I think I have explained this earlier in the example, okay? Where if you want to determine the not determine. All right. Let's say you want to do some process. Okay, to do some process to harden this surface. Okay, harden this surface. Right. You know that the theory is from the Fick's law is minus d delta c over delta x. All right. One of the application, for example, okay, this can be applied, but for what purpose? Okay, let's say you want to design a, a, a hardened, you want to determine a thickness for the hardened part. Okay, this is the gear. If you diffuse carbon, this is the gear tooth. Okay, if you want to harden the surface, you will harden this region only. Okay, this region. Let's say the concentration of this point is actually the concentration of carbon that you put inside this case hardening process. Okay, there is a carbon here. Carbon source can be from any source. Okay, depends on the process. Let's say there are carbon around it. Okay, this is the DC. Delta C means if the concentration from let's say this is the interface. Okay, this is carbon. This is the gear, which is made of iron carbon. All right, you want to harden up until this level, which is X. This is X1, this is X2. Okay, this is concentration 1, this is concentration 2. The distance here is a distance where you want it to be achieved a certain concentration of carbon. Let's say you want it to have um, 30% of carbon. Okay, ataupun there's a concentration value of carbon at this point. All right, this concentration 1 is concentration of carbon in this region. Okay, in the container of the case hardening process. All right, that's C1, and this is your objective. You say this. Okay, or you want it to have a certain distance. You can put a x1 as a 0 and x2 as a certain thickness of of the uh, hardened region. Okay, from here to here is a x0 x1. This is x2. Right. So from this from this application, basically they use to compare which diffusion flux is higher, which diffusion flux is lower. You can make a comparison in terms of process improvement, or maybe if you change the materials, okay, the materials for the gear, you can determine the J value, compare J value. So whatever you compare improvement on the process, you can look at the parameters such as the material of the gear, the concentration that you want to achieve, the distance that you want to achieve. You can compare in terms of the J value. Okay, the J value, which one is high flux or low flux, diffusion flux. So improvement in the process can apply this Fick's law. Okay, that one is steady. Okay, it doesn't count time as a parameter in the diffusion rate. But the concentration of diffusion species, if consider the function of distance and time, okay, it can apply a fixed second law. Okay, fixed second law consider the temperature changes. Okay, first fixed law, second fixed law is different in terms of the parameter, where the parameter for second fixed law is considered time, where different behavior of diffusion at a time 1 and time 2 is different. Okay, so by considering this parameter, for example, diffusion of copper in the aluminum bar, okay, it depends. If you use what we call this is not time. This is temperature. Sorry, this is temperature. Okay, but considering temperature, diffusion rate is fast, and the distance of diffusion will occur further. Okay, for example, T high is higher than T2 and T2 is higher than T1. So concentration is higher at the and the distance is farther. For example, let's take a look at this distance. Okay, at temperature 1 and temperature 2 and the temperature 3 for high temperature. Okay, high temperature, the concentration will achieve higher. Okay, because of the influence of temperature. And at the temperature T2, since T2 is lower than T3, so the concentration is less. So second fixed law is considered temperature. Okay, so different temperature will give a different diffusion rate. Okay, so if a material contains grain, the grain boundary will act as diffusion pathway. Okay, along which diffusion is faster than in the bulk materials. If you look at this schematic diagram, how far the diffusion will occur at the grain boundary compared to the grain. What do you think? Why this happened? Why is it the diffusion rate at the grain boundary is higher?
More space.
Yes.
Why is it there is more space at the grain boundary?
Defect.
Defects, yes, the defects. Okay, because it is unordered structure. Okay, ordered structure usually tend to form more packed atoms in the crystal plane. Okay, or not crystal plane, in the crystal volume. Okay, however, at a disordered structure, okay, it's less packed, more vacancy, less number of atoms, more spaces. Okay, that's the reason it requires very low energy to move from one part to another part. Okay, if let's say they are all receive all region receive similar energy, or which is temperature. So since there are abundant vacancy in this part, the atoms at the grain boundary will most slightly not faster than in the grain. Okay, this is what happened in the diffusion. So diffusion involves a net movement of atoms or molecule from region of high concentration to low concentration. And the fixed first law and second law can be used to calculate the flux of atoms through a crystal structure under a different condition. And the grain boundary provides a greater vacancy concentration, greater vacancy concentration. I mean that it has more vacancy compared to the inside the grain itself, where diffusion happen at much higher rate. Okay, I think that's all for topic 3, diffusion and solidification and defects. Okay, you are going to use this in the chapter. Uh, the next chapter is mechanical properties. Chapter 5. Chapter 5 for a phase diagram, as well as chapter 6 for the ion carbon. Okay. Any question?
No, Dada.
All right. If there's no more question, I think that's all for the